Surprisingly, the people who talk about nonlinear systems in a VUCA world and the people who call for making strategic decisions based on fixed numbers are sometimes the same people. Meanwhile, VUCA is an acronym for volatility, uncertainty, complexity, and ambiguity. In production, we deal with a network of interdependent operations resources that work together to transform raw materials into finished goods. There are usually many different items in process at the same time. To make any part, subassembly, or final product, materials must go through a series of processing steps. Therefore, it is quite clear that the factory people would like to realize how long each step and the entire process will take. And this is where the concept of lead time comes in. According to the Apex dictionary, lead time is a span of time required to perform a process or series of operations. But how any span of time can be measured or calculated? In a deterministic world, the question can be answered through the operations detail scheduling. Unfortunately, in a volatile, uncertain and complex operating environment, such as is typical for small batch manufacturing, this approach is not only useless but often harmful. Moreover, the answer cannot be unambiguous, as in a VUCA world, precise numbers can be confusing and result in incorrect implications. To clarify this point, let's consider only one processing step located somewhere in the middle of the entire system. Suppose that at this step there is only one workstation for manufacturing parts from blanks, consisting of a single machine and a storage bin in front. Let T-in be an average blanks inter-arrival time, and Tc an average part cycle or processing time, say 1.25 and 1 time units correspondingly. In deterministic world, with no volatility and no uncertainty, the lead time to produce any part would be exactly 1 time unit, and the storage bin would always be empty. However, even moderate variability can have a significant impact on the system's behavior. In this case, a queue of unprocessed blanks may appear in front of the machine, and the lead time will now be equal to the sum of the cycle time and the waiting time in the queue. If, for example, we take the simplest MM1 queuing model with an exponential distribution of both the inter-arrival time and the cycle time, the average waiting time in the queue will be 4 units under the given parameters. And therefore the average lead time will be 5 units, which is 5 times the average cycle time. The appropriate formula was obtained by John Kingman in 1961, and its most important feature is the nonlinear relationship between the average lead time and the workstation utilization rate. In this regard, it should be noted that if U is reduced from 80 to 50% over the same cycle time, the average lead time will decrease to 2 units, while the growth of U from 80 to 90% will increase the average lead time to 10 units. Why should we be careful with this nonlinearity? Well, let's say that one process has half the average cycle time of the other. Which of the two processes will take longer? The answer to this question largely depends not only on the processes themselves, but also on the stochastic structure of demand for the corresponding resources. Look at the table with calculations based on the simplest MM1 queuing model. If the first resource with a shorter cycle is 80% utilized, while the second with a longer cycle is 50% utilized, then the average lead time for the first one will be longer. But that's only part of the answer. Look at the corresponding lead time probability distributions. For the first process with a shorter cycle, in 10% of cases, the lead time will be more than 11.5 units. While for the second one with a longer cycle, in 10% of cases, it will be more than 9 units. Which fixed numbers will you choose to configure your production management system? Especially taking the uncertainty of the relevant process parameters into consideration. Summing up all the above, let's formulate the following takeaways. The lead time primarily depends not on static characteristics such as product structure, process structure, or average cycle times, but on dynamically changing, unknown, sometimes unknowable, and therefore unpredictable ratios of resource utilizations and variability parameters at interacting processing steps. Volatility and uncertainty in complex systems cause nonlinearity and in turn ambiguity. In particular, depending on the demand placed upon individual resources, the lead time ratios may be inverse to the cycle time ratios. No lead time, regardless of whether it is called manufacturing, cumulative, decoupled, etc., can be accurately calculated and configured in advance.